We build modern software for speed. Agile and DevOps pipelines are engineered to push code into production constantly, but that high-velocity stream almost always hits a wall. The deployment suddenly halts at a single, narrowed checkpoint: quality assurance. The paradox of modern testing is that while we have fully automated the execution of our tests, the design of those tests remains a manual, fragile process. Engineers are still writing scripts by hand, one by one. Software automation expert Hans Buwalda accurately diagnosed this issue years ago. He pointed out that succeeding in test automation is a design challenge rather than a technical execution problem. Tools like Selenium or Gauge are excellent at executing commands, but when they rely on procedural, handwritten scripts, they accumulate test smells. Because the code is highly coupled to the user interface, a single update to the application's layout triggers a cascading wave of domino failures across the entire test suite. This structural fragility forces QA teams into an endless loop of script maintenance. Instead of validating new features, engineers spend their days updating broken locators, turning the quality assurance department into the primary bottleneck of the development cycle. Model-based testing addresses this by shifting the focus from individual script maintenance to a system-wide architectural paradigm. By decoupling the logic of a system from the mechanical steps required to test it, MBT moves the industry away from manual procedural scripting and introduces algorithmic test generation. At the core of this methodology is the model. A model is a precise, visual, and mathematical blueprint of the system under test. Instead of linear steps, engineers create a geometric mapping of expected behaviors, defining valid states and specific transitions. Translating ambiguous requirements into this strict logic serves as an early-stage quality gate. This process highlights missing edge cases and undefined pathways before any code is written. These models are highly versatile and generally fall into 4 approaches. The first is domain-based modeling, which acts as an intelligent filter to generate and combine valid input data for the system. The second is the environment-based approach. This maps out external call sequences and environmental factors to see how the system reacts to outside variables. The third is behavior-based modeling. This maps the complete business logic and embeds a test oracle, dictating exactly what the expected output should be. Finally, the abstract script generation approach instantly compiles high-level test specifications directly into structural code, ready for the target framework. Creating this blueprint requires upfront effort, but it functions as a proactive requirement verification engine. It isolates and neutralizes logic flaws at the very start of the software development lifecycle. Once the model is built, we introduce the engine. MBT tools, like the open-source GraphWalker, use mathematical pathfinding algorithms to read the blueprint you've created. The algorithm relentlessly traces connections between nodes, mapping every possible execution scenario. Hitting a boundary node, it extracts precise maximum and minimum values allowed. This instantly generates test cases covering 100% of defined boundaries, automating classic black box techniques. Compare this to the industry standard. A human engineer reading a specification document has to manually calculate all those precise boundaries and then type out dozens of individual scripts to verify them. The algorithm does it all instantly and flawlessly. But simply relying on raw computational power introduces a dangerous new vulnerability, known as test case explosion. Without constraints, the algorithm falls into infinite loops, exponentially spawning thousands of redundant paths. To solve this, engineers apply test selection criteria. Setting specific filters for code coverage or high-risk logic collapses the infinite possibilities into a tight, optimized sequence. The algorithm provides the brute force required to explore every pathway, while the engineer's strategic selection criteria provide the vital constraints that make the resulting suite efficient. When integrating MBT into a pipeline, teams often make a critical assumption. They assume the model itself directly interacts with the software application. It doesn't. Look at this architecture stack. In the top tier, the pathfinding algorithm outputs a logical sequence called the abstract test case. It passes down into the middle test adaptation layer, which binds theoretical pathways to real code parameters. Once translated, the concrete test case emerges. It is this concrete test case that seamlessly feeds into your existing procedural frameworks, like Selenium or Appium, to actually interact with the software. This layered architecture enables strict bidirectional traceability. If a concrete test fails at the execution layer, the system traces that failure backwards, moving through the adaptation layer to pinpoint the exact flawed business requirement in the model. This architecture means that while a UI change still requires an update in the adaptation layer, the high-level test logic in the model remains intact. Just one small adjustment in the middle tier synchronizes the entire testing suite, completely preventing the typical domino effect of script failures. The theoretical advantages of MBT are matched by empirical data from real-world deployments. During the European Testomat project, researchers introduced the GraphWalker framework to enterprise teams previously reliant on manual procedural scripts. The results showed a drastic expansion in end-to-end path coverage. The teams moved from a baseline manual defect detection rate of about 70%. Despite a steep learning curve and modeling overhead, eliminating domino script failures offsets initial setup costs rapidly. Beyond the metrics and cost reductions, we have to look at what this methodology means for the QA professional. An engineer's role evolves. They stop being a procedural script coder, tasked with writing disposable, single-use automated tests. They become an automation architect, designing intelligent, self-healing behavioral rules for the system to follow. Adopting this approach aligns quality assurance with the speed of the CI/CD pipeline, turning a manual bottleneck into an integrated, self-healing component of software architecture.